Let's work a magnetic boundary condition problem. So for Z greater than 0 is free space, so the relative permeability is 1. For Z less than 0 is a material with relative permeability of 2. On the Z equals 0 plane, we have a surface current density flowing of 8 amps per meter in the y direction, and you're given the magnetic field intensity for Z less than 0. As always, you should begin by drawing a figure. I've drawn a figure of all the pertinent information, and what we need to find is the magnetic field intensity, which we'll call H sub A, for Z greater than 0. We'll start by applying the integral of B dot ds equals 0 over this Gaussian surface. Now, the magnetic flux density field in the x direction and in the y direction, which is into the page, go into and out of the sides of our Gaussian surface. So the integral of B dot ds along the sides will be 0. S is the area of the top and bottom surface, and the top surface points in the z direction, the bottom surface points in the minus z direction. The integral of B dot ds over the top surface will be B sub az times s, and over the bottom surface it will be minus B sub bz times s. The minus sign coming about from the dot product between B and S, which are pointing in opposite directions. So B sub az is equal to B sub bz. So let's rewrite the magnetic flux density fields in terms of the magnetic field intensities using our permeabilities in materials A and B. So I've made the substitutions of mu times H for the magnetic flux density fields. Let's divide both sides by mu sub 0. And solving for H sub az, we see it's equal to mu sub Rb over mu sub Ra times H sub Zb. So substituting 2 for mu sub Rb and 1 for mu sub Ra and 5 for H sub Zb, we see that H sub az is equal to 10 amps per meter. So now we have to find H sub Ax and H sub Ay, and we're going to use Ampere's circular law to do that. So here is our Amperian loop. So the integral of H dot dl around this loop will equal the current enclosed. So the integral along this top segment will be H sub Ax times this length W. The integrals on the right and left side will have the same magnitudes but opposite signs because you're integrating in opposite directions, so they will sum to 0. And the integral along the bottom segment will be minus H sub bx times W, and the minus sign coming because you're integrating in the opposite direction that we have defined H sub bx. Since we're integrating clockwise, the current enclosed will be the current flowing into the page because of the right-hand rule, and that current will be K sub y times W because K sub y is the current flowing in the y direction, which is into the page. So we can divide both sides of the equation by W and then solve for H sub Ax. So H sub Ax is going to equal K sub y plus H sub bx. So now let's substitute in our values for K sub y and for H sub bx. So H sub Ax will be 13 amps per meter. So now we have H sub az and H sub Ax, so let's find H sub Ay. So I've redrew the figure so that you can see y in the plane of the page, so x is coming out of the page at us. So the current is flowing in the y direction. So there's no current flowing into the plane of the page. So there's no current that's going to flow through this Amperian loop I've drawn here that's in the plane of the page. So now applying Ampere's circuital law to this Amperian loop, we get h sub ay times w minus h sub by times w, and it equals 0 because the current flowing through our Amperian loop is 0. So h sub ay is equal to h sub by. So now let's just substitute in our value of h sub by, which is minus 10. So our final component, the magnetic field intensity in the y direction in region A, is minus 10 amps per meter. So that minus signs don't cause you problems, you should always work with symbols and at the end then plug in the appropriate values for your components. Collecting all of our terms, we have the value of h for z greater than 0 is equal to 13 in the x direction, 10 in the minus y direction, plus 10 in the z direction, amps per meter.